Now, in order to understand wave-particle duality better, let's have a look at 3 cases of the famous double slit experiment. Now, let's illustrate the behavior of particles with the following thought experiment. Let's say that we have a ping pong ball gun in which we fire off these ping pong balls, these particles, at 2 openings, which we can call them slit number 1 and slit number 2. Just behind on the other side we have a detector that we could use to find the probability of arrival at a certain point. In practice, this detector could be literally something as simple as a bucket in which we would collect any ping pongs which bounce off and enter this position. Now, it's important to note that we can define the probability of arrival at a certain place. So I'm just going to write down here that the probability of arrival, let's say that this is equal to the probability of arrival at a certain place as the number of particles that have been detected at the detector divided by the total number of particles which have been fired. Okay, well, let's start off with our thought experiment, and the first thing that we're going to do is we're going to look at the probability of finding a particle at a given place along this line where the detector is if we close slit number 2. So I'm just going to go ahead and close slit number 2. So if we were to plot the probability of arrival with only slit number 1 open, we're going to notice that there's quite a high chance of the particles being found directly behind the slit. In other words, as particles are fired in most directions, mainly ahead, but occasionally some of them move a little bit to the left and a little bit to the right, the highest probability is found directly ahead of the slit. So let's just plot the probability, and it's going to be a curve with a peak somewhere here. So it will peak just quite near the opening of the slit. We're going to call that curve P1. So if we are sort of here near the peak, there's a very high chance of our detector catching a particle. However, if we are sort of over here where our detector is in this little picture over here, it doesn't have to be there, but if we're there, there's a very small chance that one of these particles might bounce across and hit that precise spot. However, we're far more likely to find a particle if we are right at the center. Similarly, we can also plot the probability if we had slit number 2 open and slit number 1 closed. So let's just go ahead and open up slit number 2. So we're going to open up slit number 2, and what I'm going to do is I'm going to close slit number 1. Now, if that's the case, I'm going to get a similar curve, and the peak of that curve is going to be directly opposite slit number 2. This is the position in which it is far more likely to find a particle. So we're going to start off with quite a low probability, kind of like rising, and reaching a peak sort of opposite where slit number 2 is, and then the probability is slowly decreasing. We're going to call that probability number 2. So good. Now, what happens when we leave both slits open? Now, whenever we have some particle behavior, the probability of finding a particle at a certain space with both slits open is actually the sum of P1 and P2. We can represent this in our graph as simply adding up those individual probability curves. So in practice, our curve appears to be just a little bit larger almost everywhere. I know that my sketch is not quite incredibly accurate, so I haven't mathematically added up the two curves. However, I'm just sketching this for illustration purposes. Let's call this curve, I'm going to call that P12, i.e. the probability with both slit number 1 and slit number 2 being open. So if I'm in the region near the center, there's quite a high probability. In other words, if I'm somewhere near this region over here, there's quite a high probability of detecting a particle. However, if I'm somewhere around the side where the detector is, in this case, there's a relatively low probability. Now, to summarize, this actually leads to some of the properties of particles. So number one, for the particles, and I cannot stress how important this is, but particles tend to arrive in lumps. In other words, discrete quantities. So we can write this as particles arrive in discrete quantities, assuming of course that the particles are indestructible in this case, or our sort of ping pong ball gun is not powerful enough to actually break any of them. The second observation that is really important for our observation of particles is that they show absolutely no interference. So there's no interference. Unlike wave behavior where there is some interference. And finally, the probability with both slits open is equal to the probability of just slit number 1 open plus the probability of slit number 2 open. So we can write this as follows. Our third very important conclusion is that P12 is going to equal P1 plus P2. Now this summarizes some of the more important qualities of the double slit experiment for particles. Let's have a look at what does the double slit experiment look like for waves. Now in this case we're going to have a wave source. In practice this could be something as simple as a branch in a pool of water that we're going to be moving up and down. That's going to create some wavefronts. In other words, it's going to create some waves. Now if there are two openings, let's call that once again slit number 1 and slit number 2. That means that we might get some wave interference if both of them are open. The way we're going to measure how much of the wave has reached our detector could be with something as simple as a ruler to measure the intensity of the wave. So our detector could be just a ruler in this case, so I'm just gonna sort of draw that as a generic detector. Remember, we can measure really the intensity of the wave because we know that the intensity is proportional to the amplitude of the wave squared. So you can just write that down as the intensity is proportional to the amplitude of the wave squared. Okay, well, let's do exactly the same experiment. Now the first thing that I'm going to do is close slit number 2. Now, once again, we're going to plot the, well, not quite the probability in this case. Let's plot the actual intensity of the wave. We're going to see why we're plotting the intensity in a moment's time. So the intensity of the wave with just slit number 1 present is going to be fairly similar to what I would expect. So just opposite the opening, we're probably going to have quite a high intensity of the wave. So we can sketch that with a picture similar to this one, and then the intensity is slowly going to drop, approaching 0. I'm going to call this I1. Okay, and if we do the reverse, so let's say that we close slit number 1 and we're going to open up slit number 2. Well, if that's the case, we're going to get a pretty similar curve. So it's going to be centered near the center of slit number 2, and this is quite interesting. So it's going to be a curve which it should reach maximum right about there. So I'm going to call this I2. Okay, now let's do a really interesting experiment. What happens if both of those slits are open? Opening up slit number 1 as well. If that's the case, the wavefronts emerging from slit number 1 are actually going to interact with some of the wavefronts from slit number 2. Now the intensity is going to vary quite drastically as we move along this y-axis. What it's going to look like when both slits are open is something similar to this. Notice that there are some regions of quite high intensity and there's some regions of much lower or minimum intensity. So this is almost a strange curve, and it's really telling that something is actually a wave. We can summarize our findings for waves just here over on the side. In fact, let's leave our let our findings for particles to be also visible. So we can write down over here that for waves, number 1, the intensity can have any value. So this is really important. So the intensity of a wave can have any value. This is to be contrasted with particles arriving in discrete quantities. In other words, the equivalent of intensity in particles only has 2 values, 0 or 1. Well, not actually 0 and 1, but it's binary. Either the particle's there or it's not there. With waves, the intensity can be literally almost any number. It could be anywhere from 0 all the way up to very high intensities. Number 2 of our findings is that wave intensity seems to be proportional to the amplitude squared. So I can just say over here that intensity is proportional to the amplitude squared. And notice something really interesting, and that is, let's call that curve, that compass curve which we draw, I1 and 2. Now I1 and 2 is not equal to the sum of I1 plus I2. Now notice that this is very different from the behavior of particles. So in particles, this curve up here was the mathematical sum of the other 2 curves. For waves, that's not the case. The reason for that is that the waves interact with one another. If under certain circumstances a trough meets a peak, the waves actually cancel each other out in a way which leads to regions of minimum intensity. In other words, these dips over here are examples of destructive interference. So we can write down over here that they do absolutely interfere, and this is really important. So interference occurs. Now we have a pretty good idea of the properties of particles and the properties of waves. So let's see if we can figure out where electrons lie in the spectrum. We're going to do exactly the same experiment, the double slit experiment. However, we're going to be firing electrons at the double slits. So let's have a look at this experiment for electrons, for quantum mechanical particles. When electrons were first discovered, people were indeed wondering whether they're particles, whether they're waves, particularly at the birth of quantum mechanics. So, well, imagine that we have an electron gun over here on the left. This in practice is actually quite easy to do. All we need is a filament and we can heat it up to a few thousand volts, and when the filament is heated up, then it will start releasing electrons in multiple directions. So some of them are going to go here, 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 etc. Okay, well, our detector in this case could be something like a Geiger counter. So we have a Geiger counter, which could then be connected to a photomultiplier. That photomultiplier will increase the electrical signal, and then we can just connect it to a loudspeaker. So I'm going to say there's a Geiger counter connected to a photomultiplier. The photomultiplier is just a device which, let's just say, it increases the number of electrons, the signal, and let's say we connect that photomultiplier to a speaker so we can hear the individual electrons. Okay, well, let's do our thought experiment with let's just say slit number 1 open, just as before. Now, when that's the case, what we observe is essentially particle behavior. So we have the good old curve that we're now familiar with, centered somewhere around slit number 1, and we're going to call this probability 1. So far, so good. The electrons seem to have a particle behavior. In fact, on the loudspeaker, we tend to hear only sharp clicks of 1 intensity. So there are no half clicks, there are no 0.7 of a click. So that tells us that the electron definitely has some particle properties. And if we opened up slit number 2, but we closed slit number 1, just like that, what we're going to see is the standard curve that we now know, that is centered somewhere around the position which is directly opposite slit number 2, and we're going to call this P number 2. So in a way, this is particle behavior. So we can definitely relax. The electrons are definitely particles, and the reason they're definitely particles is because we can hear discrete clicks. Actually write this just over here on the side as some of the properties for electrons, and number 1 is that they tend to arrive in discrete quantities. So properties for electrons, we can just say that they arrive in discrete quantities exactly in the same fashion as particles. So they arrive in discrete quantities. Okay, well, let's have a look at the probability of two of the two slits being open. So what I'm going to do is go ahead and open up slit number 1 and slit number 2. Now at this point we're definitely expecting that we're going to get a curve which is very similar to the curve for individual particles such as ping pong balls, because the electrons after all arrive in cliques. However, to our dismay, if we were to actually do this experiment, what we do get is a curve which is very similar to the curve for waves. In fact, it will look something along this line over here. So we can see absolute evidence of interference. Or how can that be when the electrons seem to arrive in discrete quantities? However, they can also interfere with each other. So we can just say over here that they interfere, which is absolutely incredible. That the electrons exhibit particle behavior, yet they tend to produce this curve which is characteristic for waves. Well, one thing that we can do is we can place a detector. In fact, we could even place two detectors at slit number 1 and at slit number 2. One way in which we could place two detectors, so I'm going to call that D1 and D2. One thing they could do is that they could send powerful pulses of light with quite a short wavelength, which are going to be able to precisely tell us where those electrons are. So quite a short wavelength, so we could just sort of characteristically draw that with sort of a bluish color. So the interesting bit is that as soon as I start watching the electrons going through, I miraculously get a completely different result. So as soon as my detector is looking at slit number 1 and slit number 2, the curve which I get is actually very much similar, let's draw this like this, to the standard curve we would expect for particles. So this over here is the curve, this starry curve over here is the total probability of finding an electron at a certain position when we are observing. So this happens when we observe the slits over here, and this curve over here, the one in which interference occurs, is what we get when we don't observe the slits. And this is absolutely bizarre. In practice, the electrons are really fragile. So the more we want to know what their position is, the shorter of a wavelength we need to be using. But remember, the wavelength of an electron, that's the energy of light, is inversely proportional to the wavelength. So if you want to know more precisely where an electron is in space, we need to use light of smaller and smaller wavelengths. So as the wavelength goes down, the energy tends to increase. So we're also disturbing it more. This effect is known as the collapse of the wave function, and it's one of the biggest mysteries of quantum mechanics. The very fact that our observation seems to so drastically change the outcome of our experiment is absolutely fascinating. The great physicist Richard Feynman did a famous logical proposition. So I have this proposition over here, and let's say that we can just propose that each electron either goes through slit number 1 or slit number 2. Well, if we were to block, let's say slit 1, so if we were to block slit 1, what we're going to do is we're going to get P1. So this is something which is really interesting. If we block one of the slits, so if we were to block this slit, we're going to get curve P1. If we were to block slit 2, we're going to get P2. However, the really interesting case is that this gray curve over here that we observe when we open the slits, that is P1, 2, this curve over here, well, that is not equal to P1 plus P2. So P1, 2 is not equal to the probability of one of them being open and the probability of the other one being open. So this proposition has got to be false. So we have refuted our proposition. The electron does not go through either slit number 1 or slit number 2. However, if we were to observe it, and if we were to place a detector on either side, then we do get that smooth continuous curve that we would expect, which is this starry curve which I've drawn over here on the side. So let's just quickly summarize the very strange behavior of electrons. So number one, they arrive in discrete quantities in exactly the same way that particles do. Number two, they interfere. However, I'm just going to add that they seem to interfere when not observed, which is very bizarre when not directly observed. And we can actually, so we can see that. In fact, that's how physicists discovered electron interference through an electron diffraction when shooting electrons through a crystal to try and study the crystal structure. Okay, and additionally, number three, so the sum of the probabilities doesn't seem to equal P1 plus P2 when the slits are not observed. However, if you were to observe this, then P1 is equal to P1 plus P2. So I'm just going to say when observed, directly observed, and for the one above, I'm just going to write down when not observed. So we can compare and contrast in this way the behavior of particles, waves, and electrons. One very final thing to add on the topic of probability amplitudes, this curve over here indicates that the amplitude of something squared seems to give you the probability of finding the electron at that particular occasion. This is what arose the concept of a wave function. We don't really know what the amplitude of that is. For example, in the case of normal mechanical classical waves, when we're talking about amplitude, we're talking about just the height at which the water rises. So it's a measurable quantity. The probability amplitude of an electron is different. We don't really know the nuts and bolts behind it. However, what we can say is that the probability of the electron going through slit 1, let's say, is equal to the amplitude of something squared. So the way I'm going to write amplitude is with absolute value. I'm going to use this letter phi to indicate this. So let's say that this is the probability amplitude 1 squared. And this is what arose the concept of the wave function. Okay guys, so once again, this video was definitely not on the A-level specification. However, I personally find this topic fascinating. What I'm going to do is I'm going to post up in the description below quite a few links to some university level courses which you guys could use to study this wonderful subject of quantum mechanics further. Thank you very much.